forward. There we go. It's tilted. Let's see. All right. There we go. So, as we were saying, for Alex who may or may not have seen this, we define the adjoint of an operator such that if omega v gives us some ket, then the bra that corresponds to it, by definition, is the operator omega adjoint, omega dagger applied to bra v, which serves to define omega adjoint. That's what we mean by the adjoint of the operator. Put in matrix form, it's the matrix which, when multiplying the row representing bra v, gives you the column, that row is the adjoint of the column that represents omega v, the ket. So omega adjoint applied to the bra is the adjoint of omega applied to the ket. Is the definition of the adjoint of the operator. We will now deduce what its matrix elements are, and then, for those of you who have taken linear algebra, I will point out all I'm saying is that the adjoint of a matrix is the transpose of its complex conjugate. Whoops. Its, no apostrophe, bad name. Its matrix elements are omega dagger sub ij, like any self-respecting matrix element, or even one that isn't respecting itself. It's that inner product, bra I inner product with operator omega dagger, inner product with ket j. Now, by definition, omega dagger, if I put it inside I here, just becomes omega, right? Because of over there, we said that omega dagger on I gives you the bra corresponding to omega I as a ket. So I can go like that. But then I can do one of these numbers. I can flip it around, and if I do that, what do I have to also do? I got to star it, right? So I can flip it around as long as I take the complex conjugate, because that's our rule for inner product, is that if you reverse the order, you get the complex conjugate. Yeah? Second one to the third one?
Yeah, so if you have that.
Yep. So if the rule is that if I pull an adjoint into a bra, you have to unadjoint it like that. Right? This was our definition, was that this was the rule here.
So I here is still a vector.
I is still a vector, right? So this is sloppy notation for this beast right here. By definition means the adjoint of the ket omega I. The bra, which is the adjoint of omega I, by definition, would be this beast right here. This is what we mean by omega I as a bra. It's the bra which is adjoint to omega applied to I.
So that I is not a new one. At first I thought it's a I component.
No, it's a specific. So I varies from 1 to n, but for any given value of I, we're looking at a particular basis vector. Any other questions? So then, I can do this. I can say, well, if I'm applying it to the ket, if I'm inside the ket, I can just pull it straight out. So I can say that this is j omega I star. said that the ket omega v is the ket corresponding to omega applied to ket v. So if it's applied, if omega is applied to a ket, I just pull it right out. But that's the matrix element omega ji star. So in other words, omega dagger ij is omega ji star. And what that means is that the matrix representing omega dagger is the transpose conjugate of the matrix representing omega. So for example, suppose omega is the matrix 1, I, 1. This time I is the square root of negative 1. It's not an index. Let's see. Actually, no, I should make it more interesting than that. Otherwise, it won't illustrate well. 1i, 2i, 1. Or even better, 1i, 2i, 3. I should mix it up in terms of so that when I do things, it actually looks different. If I take the transpose, that means to flip along the diagonal, basically, to interchange the rows with the columns. The columns of the transpose are the rows of the matrix, and vice versa. So what is omega transpose in this case? Well, its first column is the first row of omega. So the first column is 1i. And the second column is the second row of omega, so it's 2i, 3. So that's omega transpose. And omega dagger is omega transpose star, the complex conjugate of omega transpose, which, by the way, is the same thing as the transpose of omega star. It doesn't matter which order you do it. So that'll be 1 minus 2i minus I 3. So the adjoint, the matrix representing the adjoint of an operator is the transpose of its complex conjugate, or the complex conjugate of its transpose. Take it either way. But that's what we mean in linear algebra. The adjoint of a matrix is its transpose conjugate matrix. And so we found that that's what we need to do in order to, if I have some matrix times a column, then if I want the adjoint of that, I have to multiply the row times the adjoint of the matrix. In linear algebra speak, suppose I've got a column V, which is a matrix. Sometimes we write a matrix with a double bar on it to show that it's something that's not a vector, it's not a scalar, it's something bigger. Suppose that V is omega W, right? Then that's that's the correspondence for ket V is operator omega applied to ket W there. So what do I do to make the column which represents the adjoint of V? If I want the column that represents V bra, what do I do to V? I turn it into a row and I complex conjugate. That is taking the transpose conjugate. Changing a column into a row and taking its complex conjugate is taking the adjoint. In matrix algebra speak, it's replacing it with its transpose conjugate. So in other words, if I want V transpose star, that will be omega W transpose star. I should just add some more brackets outside of all that. Does anybody remember what's the rule for taking the transpose of a product? You flip it. Yeah, it's the transpose of the product is the product of the transpose is in the reversed order. So this is equal to W transpose omega transpose star which is W transpose star omega transpose star, or in other words, in linear algebra speak, V dagger is equal to W dagger omega dagger. Or in other words, the reason why you need to replace the matrix with its adjoint is because, well, that's just the way matrices behave. That if I want the adjoint of omega W, that's equal to W adjoint omega adjoint. So omega adjoint is the matrix which, when multiplied by W adjoint, gives you the adjoint of that original vector V. And so, again, everything is lovely and consistent and all that. And if you haven't done this for a while, or if you've never done it, stare, 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 think, 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 until you get it, kind of into your head. Okay, any questions? Yes?
You said that omega with the two balls, it's not a scalar, not a vector.
Yeah, it's a matrix, in other words. Yeah, it's an operator. Yeah, in linear algebra, linear operators are represented by matrices. If we're in linear algebra, all the operators are linear, because if they weren't, we wouldn't be linear algebra anymore. So, some people don't bother with that. Some people just don't put anything on top of it. But I sometimes like to do that. So vectors have arrows over them, and row vectors are just represented by a symbol with an arrow over it. I'm sorry, click. Column vectors, yeah, rewind. Column vectors are rotated with a symbol with an arrow over it. Row vectors are those things with T's next to them to indicate I've transposed into a row. So symbol with an arrow with a T is a row vector. A matrix is a beast that has two bars over it, because it's not just a number, it's not a vector either, it's an operator. It's an n by n thing, and so it gets two bars over it to say, I'm a vector, or something like that. And the rule is that if you want to take the dagger of a product of matrices, it's the product of the daggers in the reverse order. That's just the way that it works out. That's the rules for matrix multiplication. Imply that, you can convince yourself of that by using summation notation to show that, in fact, that's the way that it works out. Okay? And any other questions? All right. So now, some definitions which are really, 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 really important in quantum mechanics.
Oh, yeah.
By the way, they're really important.
And we have only 10 minutes to go, by the way.
Yeah, that's right. Not a problem.
Okay.
I'm tired of writing definition. So definition 1,000,004. An operator is permission if it's its own adjoint. The permission operator is its own adjoint. So in other words, it's its own, as a matrix, it's its own transposed conjugate. It is anti-Hermitian if omega dagger is minus omega, and it is unitary if U dagger U, and we often use U to stand for a unitary matrix, if U dagger U is equal to U dagger is equal to I. Or in other words, if U dagger is the inverse of U, the operator is unitary. Got to sort of ring to it. If U dagger is the inverse of U, U is unitary. So I guess there's U, and if you invert U, then there's something like that. It's ridiculous. Okay, I should really, sometimes I should learn to filter. But anyway.
Can I have a little question?
Yes.
Is that a guy named Commission?
No, there's a guy named Hermit, though.
Oh.
Right?
And he invented all this stuff.
Yeah, right. Yeah. I hardly see that credit for it. So, yeah. Alex knows all the history, right? Not this one, darn. Okay. I'm pretty sure, he said, putting it on video, that Hermitian polynomials, it's the same guy as Hermitian operators and all that sort of thing. Remember the Hermite polynomials for the harmonic oscillator? I think it's the same guy. I don't know it's the same guy. I'm sure Wikipedia can tell you, because it's always right. So, any other questions? If I don't know the answer, I'll just make something up. I think that's right, but I don't remember for sure. Unitary operators preserve inner products. And by the way, jumping ahead, the reason why this is so important for Hermitian operators is we'll see that Hermitian operators always have real eigenvalues, and that means any operator in quantum mechanics that represents a physical quantity will be a Hermitian operator, because it will guarantee that its eigenvalues are real, and therefore if you make a measurement, you get a real number as a result of that measurement. So we like Hermitian operators because all the operators that represent physical quantities in quantum mechanics need to be Hermitian operators. They have to be their own adjoints. Unitary operators preserve inner products. If V1 prime is some unitary operator times some ket V1, and V2 prime is some unitary operator times ket V2, then the inner product of V1 prime with V2 prime is equal to the inner product of UV2 with UV1 vector here on the left inside the bra, I'm going to pull u outside of it. When I do, it comes out not as u, but as u dagger. So this is v2 u dagger. If I pull u out of this ket, it comes out as u. And what's u dagger u? Yeah, that's kind of fun, right? If I take u and u dagger, I can get I, right? So I take u and your dagger, and it's me. Weird, huh? U dagger u is I. So in other words, the inner product of v2 prime and v1 prime is the same as v2 and v1's inner product. So it preserved the inner product. Operate on two vectors with a unitary operator, and the results have the same inner product as the original vectors did. But wait, there's more. How much would you pay? Don't answer yet, because at no extra charge, I'm going to throw in the following theorem. Really, even in my notes, I stopped numbering them. I guess I got tired of it. So, theorem 606, or whatever you like. Theorem: the columns of a unitary matrix are orthogonal. In other words, if I have a matrix representing a unitary operator, all the columns are a bunch of vectors that are perpendicular to one another, or at least orthogonal by the generalized sense of their inner products with one another are 0. And so are the rows. Theorem: the columns of a unitary matrix are orthogonal. As are the rows. Proof. By the definition of the matrix product, the ijth element of u dagger u is, well, remember the rule for multiplying matrices is the ijth element is the ith row of the first matrix dotted with the jth column of the second matrix. So this is ith row of u dagger dotted with jth column of u. But the ith row of u dagger is the ith column of u star. Because the dagger is the transpose conjugate. So you replace columns with rows, rows with columns, and take their complex conjugates. So the ith row of u dagger is the ith column of the matrix u star. Well, I might as well just say the ith column of u star, because if I star a matrix, that's the same thing as starring all of its elements one by one, dotted with the jth column of u. But this matrix is unitary, so what is u dagger uij? It's unitary, which means this product is the identity, and so u dagger uij is identity sub ij, which is the Kronecker delta, right? Delta ij.
Which is either 1 or 0.
It's delta ij. since by definition, U being unitary says the product of U dagger with U is I, and so therefore its matrix elements are the matrix elements of the identity, which is delta ij. 1 if the subscripts are equal, 0 if they're not. The matrix where it's 1 along the diagonal, 0 everywhere else. So notice then that, well, this is the end of the proof, because this says if I take the complex conjugate of any column of U and take its dot product with any other column of U, I either get 0 if it's 2 different columns, or 1 if it's the same column. And so that's what we were trying to prove, that they are, the columns are orthogonal. In fact, they're orthonormal, as a matter of fact. This is saying exactly that. Take any 2 columns of my unitary matrix. Remember, our dot product always takes the complex conjugate of one of the vectors. So take the complex conjugate of any column, dot it 1 by 1. With any other column in there, you either get 1 if it's the same column, or 0 if it's a different column. So therefore, the columns treated as vectors are an orthonormal set. They're perpendicular to one another, and their lengths are 1. So, unitary matrices are matrices which have their columns representing an orthonormal basis, in other words. Okay, any questions? So, what we're going to do then is, next time from this we'll deduce that what unitary matrices do is they take a basis and turn it into another basis. They have the effect of rotating, so to speak, bases into one another. In the space of arrows, the unitary matrices are the rotation matrices. And the inverse of a rotation matrix is rotation by the opposite angle, go in the other direction. Well, in fact, you just take the transpose of the matrix you can show in order to do that. The transpose of a rotation matrix is its own inverse. And we've already seen an example of that. If I take cos theta minus sine theta, cos theta, if I take its transpose, I get cos theta minus sine theta, cos theta. And when I multiply it by itself, I'll get cosine squared theta plus sine squared theta type of thing. And so I'll get 1, basically, back out of it. So we'll do that next time. But anyway, that'll be the point. What unitary matrices do is they change one orthonormal basis into another orthonormal basis. We like this in quantum mechanics because it's all about eigenfunctions of operators and so forth, and we'll find that the eigenfunctions form an orthonormal basis, and unitary matrices take one orthonormal basis and another orthonormal basis, and it'll be grand and glorious and great and wonderful and something to look forward to. What's that? No, it's still going. It's still going. So let's all celebrate that Alex gets to see the end of class. 1, 2, 3. Yay!